Hi, this is the final review for Chem 216. I'm going to be going through stuff from the first three tests briefly. You can go back to the old reviews, and then focus a little more on the new material. All right, so just a little information on the schedule. On Monday, June 8th, I have office hours from 11 a.m. to 1 p.m. There's also SI from 4 to 5 p.m. In addition, there's a quiz during our normal lecture time. On Tuesday, June 9th, I have office hours from 3:30 to 5:30 p.m. And then on Wednesday from 11 a.m. to 1 p.m. The final will be on Sapling from 2 to 4 on June 10th. It's only available during that time. You'll get an hour and 30 minutes. Okay, a little bit longer time, but not a lot more. It's 60 points. 20 to 25 questions, each worth 2 to 4 points. About a quarter of the content will be from the first test, quarter from the second test, quarter from the third test, and then a quarter from the new material. Here are the lessons numbers. We'll go through them in a little bit. All right, so our first test was all about thermodynamics. So what is thermodynamics, right? Thermodynamics is all about the energy and heat related to a chemical reaction. We started off talking about thermochemistry, that's just about the heat. And we talked about reactions being either exothermic or endothermic, where exothermic means they give off heat. Think of fire. Whereas endothermic means they absorb heat. Think about the opposite of fire. Maybe water freezing to form ice. That's endothermic. All right. So energy is the capacity to supply heat or do work. And we have this first law of thermodynamics, which says that it's also known as law of conservation of energy. Energy can't be created or destroyed. It can just be transferred. So for instance, delta U, which is the internal energy, equals Q, which is heat, plus W, which is work. All right, so then in this these lessons 1 through 6, we're all talking about a bunch of different terms, right? The first ones we talked about were delta U, which is internal energy, Q, which is heat, and W, which is work. Okay, these are related via this equation. We talked a lot about heat because heat we can find from calorimetry. Okay. After this, we started talking about delta H, delta S, and delta G. We'll talk a little bit more about these after we're done talking about calorimetry. Okay, so what is calorimetry? Calorimetry is when I look at a method to figure out the heat transfer during a reaction or a process, right? A lot of times we use what's called a calorimeter, right? In lab, typically we use a coffee cup calorimeter, where basically you have some water and you add in some material. Let's say it's a piece of metal, okay? And if this metal is hotter than the water, heat's gonna go out, okay? If it were the opposite and the metal was colder, heat would go in. This would be called an exothermic, this would be called endothermic. And we always talk about our system versus our surroundings. In this case, this is our system. And the water, that's our surroundings. And so we say that Q of the system equals negative Q of the surroundings. What that means is that if this loses heat, the water has to gain the heat. And we talked about a couple things like heat capacity. Heat capacity is C equals Q over mass delta T. Okay, this is specific heat capacity. And so we could rearrange this to get Q equals C times mass delta T. Right? So plugging that in there, if we had a calorimetry problem like this with a piece of metal, it would be C of my system times the mass of my system times delta T of my system equals negative C of my surroundings, usually that's water, mass of the water, and delta T of the water, okay, or the surroundings. Now, in a problem, we would know 5 of these things, and we need to know the other ones, right? And remember that if it's exothermic, the temperature of the water is going to increase. If it's endothermic, the temperature of the water is going to increase or decrease. Okay, this was for a piece of metal, but let's say we had a reaction and we put that in there. Now, my reaction is my system. And so Q of the reaction equals negative Q of the surroundings. So we don't really have heat capacity, but we have Q for that reaction. And we end up not using Q, but we use delta H. Delta H is the enthalpy of our reaction. All right, let's go to the screen. So here we have it for lesson number 1. On lesson number 1, we talked all about heat, specific heat capacity, and molar heat capacity. Then we talked in lesson 2 about calorimetry. Remember, Q system equals negative Q surroundings. And then for reactions. We also talked a little bit about bomb calorimeters. I wouldn't focus too much about that. We have heat of solution and heat of combustion. These are 2 types of reactions we can use in calorimetry, where heat of solution is dissolving substances and heat of combustion is burning substances. We then talked a little bit about thermodynamics, and that got us into enthalpy, our delta H. We can talk about standard enthalpy. That's this with this not sign here. That means it's under standard conditions. 1 atmosphere, 1 molar, 298.15 Kelvin, etc. Delta H is in kilojoules per mole. Right? And we have here some different types of enthalpy. Now, one thing to remember is that these are always per 1 mole, right? Because it's kilojoules per mole, the amount of heat in kilojoules per 1 mole. So we talked about enthalpy of combustion and enthalpy of formation a lot. Get used to enthalpy of formation. And for instance, if I talk about H2O's enthalpy of formation, that's going to be from its constituent elements, that's hydrogen and oxygen, in their standard state, which is O2 or H2 and O2. Oops. Heat of formation is very useful because we can use it in something called Hess's law, right? Hess's law says we can use delta H's and basically put them together to figure out delta H for a bigger reaction. And here, this is one use of that, using delta HFs, which we can use a lot of times in tables in our book, etc. We can use that to find delta H for a reaction. Then we went on. Heat makes sense, right? Heat makes sense. We heat up water, we bake a cake by heating it, etc. The second thing we talked about makes a little bit less sense, and that's S, entropy. And we talked about delta S, which is the change in entropy of a system, right? And so delta H and delta S, right? These are 2 of our important things in thermodynamics. And so delta S tells us, hey, if something is getting more disorganized, that means delta S is positive. If it's getting less organized, or more organized, so less disorganized, it's negative. We have a similar equation to that one for delta H for delta S. Okay, so let's look at a reaction really quick, and let's talk about H2O going to form H2O. So H2O liquid going to form H2O solid. This is freezing. Okay. So what do I know about H2O liquid going to H2O solid? Well, I know that if I want to freeze water, I don't heat it up, right? If I have water right here, I want to go ahead and freeze this. I'm not going to put it on the oven. What I'm going to do is I'm going to put it in the freezer, right? Because what that does is that takes away heat, right? All right, so this would be a negative delta H. Okay, it gives off heat. Okay? Now let's think about delta S. Okay, what's going to happen here? My delta S, I'm going from liquid to solid. So liquid, this liquid is fairly disorganized in comparison to the ice I have in there, right? It's going from something where these liquid molecules move around to something more organized. So it's becoming more ordered, so less disorder. So in this case, my delta S is also going to be negative. All right, now we can use delta H and delta S to figure out something else, delta G. Delta G is related to delta H and delta S by this equation. Delta G equals delta H minus T delta S. So it depends on the temperature. And if delta G is negative, that means it's spontaneous. If it's positive, that means it is non-spontaneous. All right, but I can't say anything about this, right? Because I need to know the temperature. Okay, so does this occur at room temperature, right? If I add some water and I put it out at room temperature, am I gonna get this occurring? No. So at 25 degrees C, which is about room temperature, that means this is non-spontaneous. But let's say if I was negative 25 degrees C, like in the freezer, then this would be spontaneous. So delta G, which tells me about spontaneity, depends on the temperature, delta H, and delta S. All right, so on the screen, this is where we talk about that, and we talk about it, and we can also use this equation down here to figure out delta G for a reaction. Okay, so that was lessons 1 through 6. That's 25% of the test. It's on thermodynamics. We talked about calorimetry, and then we talked about delta H, delta S, and delta G. After that, after thermodynamics, we started talking about kinetics. So what is kinetics? Kinetics is the rate or speed of a reaction, right? So let's say I have some reaction A plus B going to C. This can be a fast reaction or it can be a slow reaction. We talk about kinetics and we talk about the rate of a reaction or the speed of a reaction. Now, the rate of a reaction, this reaction I can either say based on the amount of A, B, or C, right? So the rate of A would be negative dA over dt, right? It's how much the concentration of A is changing with time. For my C, it'd be dA over dt, right? This one's not negative because this is increasing, and rate always has to be positive, right? So seeing that A is going to decrease in this case, that means it's negative, right? And so if I were to make a plot of concentration of A versus time, it would decrease, whereas C would increase. So A decreases, C increases, and I can look at this and I can say, all right, I can look at this rate and I can say some things, right? First of all, this is what we call the initial rate. Okay? At any given time, we can talk about it instantaneous rate. And then I could take an average over time, and I can do this by the old trick of rise over run, and that would give me my average rate. Okay? But the rate of A and C are related. Okay? All right, let's look at this on the screen. So we talked about reaction rates. We said that they're always positive, they vary with time, and we can relate the reaction of one to another. And this is called differential, or this is, they're related via this reaction, right? Where we take into account A and B, where A and B are our coefficients in front. All right, so then we moved on to differential rate laws. And differential rate laws just say that I can relate the rate of any reaction to K, which is called the rate constant, times the concentration of A and B, these are my reactants, raised to some power. Okay? This is where it gets tricky. When we are talking about kinetics, okay, which is all about the speed or the rate of reaction, we don't know the values for M and N, okay, except in very specific cases, right? Usually we have to find these from an actual, from an experiment. And one way to do that is what's called the initial rates method, where basically, oh, by the way, M and N are usually 0, 1, or 2. They could be something like 3 or 4 also. K has variable units, but the units for rate is always molarity per second. All right, so the initial rates method, what we do is we do the same experiment multiple times, and we see how changing the concentration changes our rate. And from that, we can solve for our rate orders, M and N, and then we can plug those in to find K. All right, then we went on and we talked about the integrated rate laws. So for integrated rate laws, what we do is we integrate that reaction we just talked about, and we get these terms. These are for 0, first, and second order, okay? And notice how they always talk about the concentration of a compound at a given amount of time. And this is dependent on a couple things: our initial concentration and also our rate constant. These give us different straight lines, right? So for 0 order, if I plot concentration versus time, I'm going to get a straight line. But if I plotted anything else versus time, I wouldn't. Now, for first order, if I plotted concentration versus time, I wouldn't get a straight line. But if I plotted ln of A versus time, I'd get a straight line. And my slope would equal to negative K. That's in both of these first two cases. Okay, so if I had a second order reaction, if I plotted concentration versus time, no straight line. ln concentration versus time, not a straight line. But 1 over concentration versus time, then I get a straight line. This time, my slope, notice how it's positive in this case, it's just equal to K. By the way, K is always positive, okay? So when you determine the value for K, it better be positive. If it's not positive, you did something wrong. Okay, then we moved on to half-life. Half-life is basically using these reactions in order to determine the time required for half of a compound to be consumed. We could do this for 0, first, or second order, but we really only care about first order. So we have this equation right here. Okay, it relates our half-life to our rate constant. All right, here's a summary of information for kinetics. If you need more review, go back to the other review. All right, and here are those straight lines I talked about. Notice how if I plotted concentration versus time for first or second order, I'm not going to get straight lines. All right, now lesson 12 was about reaction mechanisms. So reaction mechanisms is how a reaction occurs. And typically it goes through what's called a transition state. A transition state is a higher energy. And the difference between our reactants and our transition state, this is our activation energy. It's always positive, okay? And then from transition state, the energy will change and decrease to get to our products, okay? This right here would be an exothermic reaction because notice my delta H would be negative. If I had an endothermic, it looks something like this. We also talked about mechanisms and rate limiting steps and intermediates and catalysts. Catalysts are very important in chemistry and in our body and in the world because they lower activation energy. Basically what this allows is for reactions that would never occur are possible thanks to catalysts. And in our body we have enzymes, which are biological catalysts. All right, so that was it for our second lesson, our second section. That's lessons 7 through 12. That was on kinetics. It seems like forever ago, but go back, study kinetics. Then we started talking about equilibrium, and we've basically been talking about equilibrium the rest of the quarter in different aspects of equilibrium. All right, so equilibrium is when, let's go ahead on the board. We said A plus B goes to C, but in reality, most reactions, or actually all reactions, are reversible. And we can relate this reaction based on a big K, not a small k, which is a rate constant, a big K, which is the equilibrium constant. And this is related to products over reactants. So that's going to be C over A and B. Okay? Now there's one other trick. If these are my coefficients, these all get raised to those coefficients. Notice how, remember earlier when I was talking about rate laws, I said, we don't know the values for M and N. Here we know them based on the reaction. Okay, so let's look at this in practice. Let's say we have H2O gas going to H2 gas plus O2 gas. This is not balanced, so I need to put a 2 here and a 2 here. Okay, so the K for this would be H2 squared times O2 over H2O squared. Okay. This 2 means 2, 2, 2. Looking back at quizzes and on the test, always remember to square it. That's what really caused issues with quiz number 3. All right, so that's my value for K, but let's say instead of gas, wait, let me think. Okay, and so let's say I say that K is equal to 500. K equals 500 means that what happens is I put stuff in here and I get a lot of this. It's mainly products. Okay? Well, that would mean it'd be so far this way. In reality, I could almost call this an irreversible reaction. But if K was, let's say, 5 times 10 to the minus 4, this would mean that my products over reactants is very small, or, yeah, products over reactants. So that means I'd have a lot more reactants. So that means it'd be mainly reactants. We said that K can vary from anything from 0, which is all reactants, to infinity, which is all products. And right in the middle is 1, which was where my reactants equal my amount of products. Okay? I know it's weird that 1 is halfway, but remember it's a ratio. All right, let's talk about one other thing with this, and that is that if this was liquid, we wouldn't even include it in our value for K, right? Because we only include in the value for K gases or aqueous. And we usually use molarity as our concentration. Okay, so that's K. We also have Q, which is, K is at equilibrium, Q is not at equilibrium. And so what happens is if I have a Q here and a K here, it's going to shift from Q to K, always from Q to K. Right? In this case, I would shift towards the right, which means I'd form more products. All right, let's go through it on the screen. So we talked about equilibrium. We talked about equilibrium constant. Then we talked about Le Chatelier's principle. Le Chatelier's principle says, hey, if I have a system at equilibrium and I stress it or change something, it will shift to counteract that change. All right, then we talked about equilibrium calculations. We talked simple and hard. The simple is if I can assume x is small. This is when Q and K are close to each other. Typically, this is when both are less than 0.01 or both are larger than 100. Okay. It's not always the case, but usual. All right, go back to the review if you need help with this. Remember ICE table. On quiz number 3, I saw a lot of people trying to do this, or some people trying to do this without an ICE table. Most of the time they got it wrong. Draw out the ICE table. I do every time I do it, so you should do it every time you do it. All right, here's some other videos if you want. You can plug in these HTTP. You can't click on these. You have to actually go in and copy those down. And then we talked about connecting free energy to equilibrium, and we can do it via this equation. All right. After that, we started talking about acids and bases, and we talked about acids and bases for a long time, long time, it seems. And so let's talk about acids and bases. Right? Acids produce H+. Okay? So if I have HCl, and I tell you it's an acid, it's going to form H plus Cl minus. If I told you that, oh, C2O2 is an acid, it's going to produce H plus and C2O2 minus. It doesn't matter which way I put these, but what happens is it produces an H plus, and if this was neutral, it becomes negative. Right? But let's say I were to tell you that HCl is a base. Okay? It's actually not, but let's say I said it was. In this case, it would have to gain an H plus to become H2Cl plus. And where does it gain it from? It gains it from water. Okay? This would be what a base would do. Okay? We can justify or talk about acids and bases based on their acid ionization, base ionization. This gives me Ka, and this gives me Kb. All right, then we talked about pH calculations. Remember, neutral is pH 7, and that's where H plus and OH minus equal each other. Acids have more H plus, bases have more OH minus. Bases have pH above 7, acids below 7. And they are related to each other based on these equations, including this key one, where Kw equals H plus times OH minus, where Kw is the autoionization of water right here, and it equals 1 times 10 to the minus 14. All right, so Ka tells me how strong it is. So a big Ka means it's strong acid. A small Ka means it's a weak acid. A big Kb means it's a strong base. A small Kb means it's a weak base. Ka and Kb are related for conjugate bases via Kw. All right, then we went into the pH, finding the pH of a strong acid, base, weak acid, and a weak base. Okay, it varies based on it. Remember that for a strong acid, whatever I get for my acid concentration tells me my H plus concentration. So if I had 0.5 molar HCl and this is strong, then I would get 0.5 molar H plus. And I can use that negative log H plus to find my pH. It's similar for strong bases, except I need to convert from OH minus to H plus before I find pH. Weak acids and weak bases, I need to use ice charts to find. We also talked about polyprotic acids. Polyprotic acids are ones that produce more than one H plus. Okay? For instance, H2CO3 loses one H plus, and then it loses another H plus. These are Ka1 and Ka2. All right, so that is it for the section 3 material. That's lessons 13 through 21. Okay? And it was all about equilibrium, all about acids and bases. All right, so the last section, which is lessons 22 through 26, we talked about specific things about acids and bases, and then we talked about some other types of equilibrium. So the first thing we talked about were buffers. Buffers are when I have a solution of a weak acid and its base, and they resist changes in pH. Okay? We have this Henderson-Hasselbalch equation here that relates the pH to the pKa of our acid and either the molarity or the moles of my acid and my base. And buffers work by basically removing any added acid or base. Okay. At the bottom I say we want to have a buffer that has a pKa close to pH, and we want to have usually a 1-to-1 ratio between the two. So let's look at this on the board. So let's say I have some base, A minus, and some acid, HA. Okay? These can be anything, such as HF, NF minus, or NH4 plus, and NH3. These are my acid, these are my conjugate base. Because what's the difference between the two? An H plus. Now, in order for these to be buffers, they need to be weak acids. Okay? And these end up being weak acids, so they have equilibrium. If this was HCl, going to Cl minus plus H plus, this would not be a buffer. Why? Because it's a strong acid. All right, so these two compounds here, well, either the HF and F minus, that's a buffer, or NH4 plus and NH3, that's a buffer. If let's say I had NH4 plus and F minus, not a buffer. Okay. All right. So the Henderson-Hasselbalch equation says that I can relate these. pH equals pKa plus log of F minus over HF. Okay. I can either use moles or molarity. Okay. Where pKa, by the way, is negative log of Ka. All right, so that's it for buffers. Look it over. If you have questions, come to office hours, come to SI, email me, and let me know. All right, then we went on and we talked about titrations. There are 4 types of titrations we talked about. A strong acid with a strong base. In this case, we start off at a low pH, because the strong acid is my analyte. And the strong base, that's my titrant. That's what I'm adding. Okay, if I add instead a strong base and I added in strong acid, I would get a opposite reaction, okay? Or opposite curve. It'd be a little more like that, actually. If I had a weak acid and start off with a weak base, I'd see something a little bit more like this, okay? Where my pH starts to increase a lot, and then I get to a region called the buffer region. And in this buffer region, the pH doesn't change as much. Okay? All right, and our fourth type, let me get my pen color back, is a weak base, and then I add in a weak acid. And in this case, we end up with the flip of case number 3. And again, we have that buffer region right here. Okay. Now, the key point, okay, and in the middle of this buffer region, at this point here, the pH equals the pKa, right? So I could go ahead and I could look over here, and let's say the pKa, or the pH was 3. That means the pKa for my acid is equal to 3. All right, there's one other, or actually a very important point on here, and that is the equivalence point. The equivalence point is where I have equal amounts of H plus and OH minus. And I can go ahead and I can look down here, find the number of mLs, and that is the volume where they equal. So I can use this volume to figure out the moles of the acid or the titrant, okay? And then use that to figure out the moles of the analyte, and then figure out the molarity of the analyte. We also talked about pH indicators. For pH indicators, what I always want is I want something that's going to change colors at the pH of this equivalence point. So let's say that this equivalence point here is at 9. What I want to do is I want to find an indicator that changes color around 9. All right, then lesson 25, we talked about solubility. And so for solubility, what we're talking about is we're talking about a solid going to form aqueous, right? So for instance, NaCl going to form Na plus and Cl minus. We can talk about a KSP here, which is equal to the concentrations of those two ions. Okay? The common ion effect means I can reduce the solubility of something by adding in one of these ions. Okay? Also in solubility, we talked about molar solubility and mass solubility. Let's go ahead and do one on the chart, or on the table. So let's say I have BaCl2, and I tell you that it has a KSP of 4 times 10 to the minus 9. 4.0 times 10 to the 9. All right, so the first thing I always have to do is I need to say, hey, what's the reaction involved in this? It's BaCl2 going to form Ba2 plus 2Cl minus. Why is it Ba2 plus? Because I can look at the periodic table and I see here that barium is in the second column. That means it's 2 plus. Whereas chlorine's in the same column as F, and those are always 1 minus. Those are called halogens. Okay? So my BaCl2 goes to form Ba2 plus 2Cl minus. These will be aqueous, and this will be solid. Okay? BaCl2 goes to form Ba2 plus 2Cl minus. Okay? All right. Now, if I wanted to figure out the concentrations of these two ions, what I could go at is I could do an ice table. All right. And if I start off with 0, okay, that means my Q is going to be 0. Okay. And that means that this is going to be plus x, this is going to be plus 2x. So at equilibrium, I'm going to get x for this and 2x for this. All right. So what is the equation for my K? My K is going to be Ba plus, or Ba2 plus, times Cl minus squared. Why squared? Because this 2. Okay. Notice BaCl2 isn't in there because it's a solid. So I could plug in these x and 2x squared. And this is going to equal 4 times 10 to the negative 9. I'm going to keep this right here, x, 2x. This is at equilibrium. And I'm going to use this KSP, right? The KSP is just the same as any K, but we're told that this is a solubility product. So I'm talking about the solubility or going into aqueous for this. All right, so KXP in this case equals x times 2x squared, and this equals 4 times 10 to the negative 9. All right, this 2x, I have to square it all. So that means it's going to be x times 2 squared times x squared, so that'll be 4x squared equals 4 times 10 to the negative 9. Or 4x cubed equals 4 times 10 to the minus 9. X cubed will be 1 times 10 to the negative 9. I could do the cube root of this. Figure out how to do this on your calculator. And I get, I think it's 1 times 10 to the negative 3, but I want to check. Yeah, 1 times 10 to the minus 3. Okay? That's my value for x. Once I found the value for x, I can figure out my concentration of barium, my concentration for chlorine. Remember to include that 2x. Okay? And I could also figure out the molar solubility. The molar solubility is the number of moles per liter that will go into solution. And that's equal to x. And so this is 1 times 10 to the minus 3 moles per liter. What that means is if I put in, I have a liter of water, I could put in 1 times 10 to the minus 3 of this, and it'll go into solution. If I put more than that, it won't go into solution. Or some will go into solution and some won't. Right? I'll end up with some solid on the bottom. Okay, if I want to do mass solubility, that's equal to the molar solubility, which is moles per liter, times the molar mass. The moles will cancel out and I'll get grams. So that'll be 1 times 10 to the minus 3 moles per liter. I don't know the molar mass of barium chloride off the top of my head, but I can find it from periodic table. 208.234 grams per mole. Boop, boop. So I get 0.21 grams per liter. So what that means is if I had a liter of water, if I put in 0.1 grams, it's all going to dissolve. So 0.1 grams, all dissolves. If I put in 0.2 grams, all dissolves. If I put in 0.21 grams, it's all going to dissolve But if I put in any more, if I were to put in 0.25 grams, some of it will dissolve, and some doesn't. Okay? The reason being is this, mass solubility just tells me the maximum amount, right? It's kind of like a fire department occupancy rating. That's the maximum amount. This room only seats 100 students. If there's 102, 100 can enter and 2 have to stand outside. Okay? We would call these two unsaturated. Okay? Unsaturated means I have less ions than I could have, right? This would be like a 100-seat auditorium that only has 20 people in it, right? These two we would call saturated. Saturated means that it has the maximum occupancy of ions, right? That would be a 100-seat auditorium with 100 people, okay? We also have what's called supersaturated. Supersaturated would mean if that 100-person room, all of a sudden 120 people get in there, right? That 120 people, there's too many. So if the fire department comes, they'd say, get out, get out, get out, right? And that getting out, that would be precipitation, right? If there is too much ions, what happens is those ions come together and they form a precipitate. And that precipitation is all by comparing Q for our equilibrium to our KSP for equilibrium. All right, and then our last chapter is on electrochemistry, right? You probably just saw this, so it's the freshest in your mind, but this is all about looking at redox reactions, okay? So in redox reactions, we have a loss or gain in electrons, and when we lose or gain electrons, we have to have both, right? So we have electrons moving, and so what we do is we separate these two, reduction and oxidation, and we have electrons moving, and that electrons give us electricity. Okay? We can tell what's going to happen based on standard cell potentials and reduction potentials. Okay? So let's show this on the board. So let's say I had Pb2+. This is lead 2+. If this were to gain 2 electrons, it would just become lead, right? Because electrons are negative, so if I have electron, 2 negative plus 2 positive, I get something that's neutral, okay? This would be called reduction, because reduction involves gaining electrons. If instead my Pb2+ were to lose electrons, it would become Pb4+. Here are those 2 electrons leaving, they're products. This is called oxidation. Okay? This is the basis for electricity and a lot of batteries. Okay, so let's say I had this, and I had tin 2+ plus 2 electrons going to tin. Okay? These are both reduction reactions. And what we can do based on comparing these to some standard electrode is we could come up with reduction potentials. This is the voltage that this reaction gives us if I join it with another electrode. So this will give me negative 0.1262 volts. This gives me negative 0.1375 volts. Okay? So what happens is, if I had a tin electrode, in a solution containing tin 2+. And I had a lead electrode containing Pb2+, right, in a solution with Pb2+, and something else. Let's say there's chlorine in there also. The chlorine really doesn't matter. If I were to put a wire between them, and then also put a salt bridge, this would allow for a circuit to go. What's going to happen is electrons are going to transfer between these, right? They're either going to go this way or this way. We can tell which way they go based on looking at these reduction potentials, okay? So, the one with the greatest reduction potential is the one that gets reduced, okay? So which one has the greatest? The lead 2+. So this gets reduced. Therefore, this one will have to be oxidized. All right, so this one gets reduced, this one gets oxidized. So what's going to happen is the tin is going to go to tin 2+, the lead 2+ is going to go to lead, and electrons are going to move in this direction. Okay? So if I want to see the reaction occurring, this right now is a reduction reaction, so what it actually is it gets flipped. And now this is an oxidation reaction. Okay? So I take this plus this. I get tin solid plus Pb2+ aqueous. How do I know this is an aqueous? Because if it's ever got an ion, if it's ever an ion, that means it has charge. It has to be aqueous. This will form tin 2+ aqueous plus lead solid. The electrons cancel out, and this is my reaction. And I can figure out the cell potential, right? That's the voltage I'll get through here by the difference between these two, right? It'd be negative 0.1262 volts minus this one. And that's going to get me 0.0113 volts. Okay, that's not a lot of voltage, right? This wouldn't be enough to power your cell phone or power the computer or anything like that, right? We'd need to have something with more voltage to work. All right. That is it for electrochemistry. I'm just going to put that on the screen again. You can see here, this is the equation for relating them. A lot of times we have a chart, so we kind of have to use that to find it. All right, with that, I will say farewell. I'll talk to you later. Remember, office hours are, sorry, I was going to have to go all the way to the back, or the front. Probably an easier way. Office hours from 11 to 1 p.m. on Monday, June 8th, 3:30 to 5:30 on Tuesday, and then 11 a.m. to 1 p.m. on Wednesday. There's also SI from 4 to 5 on Monday. If you can't make any of these, just email me. I'll try to reply. Usually I reply within hours. On finals week, I try to do it as quick as possible. All right? Talk to you later. Bye-bye.